Hello. So, in this video, we're going to be tackling one of the sort of really broad areas in calculus. So this application is optimization. Our goal is to sort of understand how to tackle optimization problems. But it's worth a note here that optimization is a entire area of study in mathematics, like even at the graduate level. And in fact, what we even mean when we say optimization can vary massively depending on exactly sort of the setting or circumstance. So our goal here is to sort of give a sequence of steps that will provide sort of a general framework on how to tackle these optimization problems. But sort of as a place to start at sort of our level, as mentioned, like optimization can span a lot of depth in terms of mathematics involved. So for us, optimization, sort of at the heart of it, it's this idea of trying to get some best result, whatever that means, given some sort of constraint that's sort of preventing us from getting sort of some extreme thing as a result. So I realize very vague terminology here, but we'll see what I mean here in a moment. So for example, let's say, you work for a company that sells soup. Sells soup in a bunch of different, by volume, right? Like certain size containers. And you're hired to figure out how to design those containers. So the question is, okay, how do you figure this out? What do we need to know? And like, what do we mean by, designing these containers to what end, right? So this is the general idea. So you're trying to get some best result. In your case, right, you're trying to figure out how to get the smallest cost involved. So the thing you're trying to optimize is to get the least amount of cost to make a container as possible. But you have a constraint to what you're doing, which is that you need to have at the end of the day a container that can hold a certain particular volume of soup, right? So you can't just be like, I'm going to have a cost of 0 by not making a can. Ha, I win, right? Like you have to actually have a certain amount of size that you can hold, and this is sort of the crux of the problem. So optimization, as we mentioned, can span a lot of things. So trying to develop a lot of, a sort of framework to work in is difficult because your optimization can involve things like maximizing volumes, minimizing costs, finding the fastest path, maximizing profit, balancing fuel efficiency and speed. Like these are all classic areas that you might look at optimizing and trying to develop some guidelines, right? Some process of steps that would sort of largely apply to all of these vastly different situations is pretty difficult. So we are going to go and give a number of steps that sort of work your way through a given optimization problem, but realize these are more like guidelines, right, than actual rules. And some will apply and some may not apply given different situations, okay? So in general, first step, sketch a picture. So this is one of those things that people like to sort of skip over because they're like, I don't need a picture, I'll just picture it in my head. But it turns out that this can actually be very, very useful. So you can draw a literal sketch of the thing, but it doesn't necessarily have to be even that, right? You could have a written out, sequence of words and sort of arrows to point which word goes to what. So the idea here is to help you sort of crystallize what exactly is involved in the problem. And in particular, this is a great way to get a bird's eye view of the sort of structure or the situation that you're dealing with. So for our soup can example, we would probably sketch some sort of cylindrical can, maybe with a cool little logo or something on the side. But the idea is that we'd have sort of a thing to work from that's sort of a representation and helps us put context when we go to the next step. So the next step, applying the language of math. So the idea here is that we want to start sort of assigning variables or coming up with the sort of mathematical elements that would be involved in what we're working with. So the idea here is that it's best to sort of overdo it at this step, then that way we can sort of cut back later, because it's difficult to sort of figure out what's missing later on. So the idea here is to sort of think of anything that is sort of a mathematical aspect of what you're dealing with and assign it a letter or make a note of it so that later on you have that as a reference. And maybe you don't end up using a bunch of that stuff, but it's sort of easier once you get further along to be like, oh, I don't need this idea or this idea anymore because it doesn't apply, than to be like, there's something's missing and I can't figure out what it is. So for our soup can example, maybe we put down some dimensions for that can. So we have like height and radius, right? So we can jot those down. We could also include things like volume and surface area and, composition, knowing what the thing is made of. These are all things that we could sort of jot down as, things that might come up that might be important. Step 3, we want to relate the key ideas into an actual function or formula. So the idea here is to come up with some function that represents the information that you're trying to optimize. Importantly for this step, we don't have to worry about whatever it is that's making that optimization difficult, right? So the idea here is that we want to come up with what is often called a primary function or an optimizable function. And that's a function whose output is the thing you're trying to optimize, right? So for our soup can example, we're trying to optimize the cost. We're trying to come up with the lowest cost for something. So here, our primary function would be a formula whose output is the cost to make a can, right? I'm not worrying about the volume or the soup or anything like that yet. I'm just saying, okay, I want a formula that represents how much it costs to make a can of whatever size, okay? Step 4, now we want to determine the restraint. So here, the idea is whatever's stopping us from doing, going crazy and getting that extreme answer, right? I just don't make a can. My can is of size 0 and now it's free. So I've minimized the cost as much as possible, right? I can't do that because I need to have a certain volume. So in our soup can example, that would be the restraint. The reason we can't have a cost of 0 is that we need to hold some specific volume of soup, okay? So the volume part itself, right, the required volume, that's the constraint. And we want to represent that with whatever we could. So for example, like a volume formula, okay? Step 5, use calculus. It's a nice broad thing to say. Use calculus to find the desired absolute extrema. So often this means that what we end up doing is taking whatever the constraint relationship is, some sort of expression or equation or equality with the constraint built in, and we use that to reduce typically the number of variables in our primary function in order to get our primary function to be sort of one variable. And once we have a function of one variable, then we can use our techniques from calculus to find the absolute extrema, right? Finding the derivative, figuring out when the derivative is 0, right? Finding the max and mins, whichever one is the one we want. And again, it could have a variety of them, right? It might have multiple extrema, so this is where it's the best result, right? We want the absolute extrema, not just the local extrema. And also keep in mind, right, that often when we're dealing with the absolute extrema, right, the domain is usually key, but here the domain may not be sort of inherent to the function. It's usually inherent to what the actual situation is. So in particular, right, the domain restrictions aren't from the equation you get, but from the actual context of whatever it is you're dealing with, like the fact that you're making a can, so all the lengths have to be positive, for example. Okay, so let's go through the soup can problem sort of specifically. So we want to minimize the cost of materials for a cylindrical soup can. That's our given. The aluminum for that can, let's just say it costs 10 cents per square inch. Okay. And we want to enclose some volume of 32 cubic inches. That's our sort of goal pit. All right, so this is the statement of the problem. So let's go through our steps. Step 1, sketch a picture. We have a nice sort of can here, right? So step 2, we want to apply the language of math. So this means we want to come up with whatever variables or anything apply. So here we could put down, right, the height, h, we have a radius, r, and we might want to make notes that like surface area might be important, volume might be important, composition might be important, right? Here it's needs to be made out of aluminum. That's the cost that we have, for example. Step 3, we want to put this into some sort of primary function, right? We want to relate the key ideas into a function. So we know that we want cost to be our output. So we need some sort of cost equals a thing, right? But we're going to need a formula for this. Our cost was dependent on square inches of aluminum, right? So that means that we're going to need some way of writing down the surface area of a can. So we need to go look up a surface area, which is going to be, the outside cylinder part plus the top and bottom. And we'll get this surface area is 2 pi r squared plus 2 pi r h. But remember, this isn't the primary function. The primary function is cost. So I need to take the surface area bit and turn it into a cost function. And to do that, I want to remember, right, that the cost was 10 cents or $0.1 per square inch. So my cost is going to be 0.1 times that surface area, where that surface area is going to be given in square inches. Okay. So this is our primary function, this cost function. Now we need to determine the restraint. So the restraint, the thing that stops us from just being like cost is 0, is the fact that we need to hold 32 cubic inches. So here we need to do volume, right? So cubic inches, volume. So we can come up with the volume equation, right? We know that the volume is 32, and the volume can be given by this pi r squared h. So this gives a relationship between, really the way we want to think about this is pi r squared h, so it has an r and an h and a number. And this will allow us to sort of remove one of the variables. So in particular, right, to move to step 5, we want to solve for, we could really solve for R or H. Here we're just going to solve for H using the constraint, and then plug that into the actual cost function. So I realize this looks sort of awful, but all we've done is plug in what H was and then simplify a little bit to get to this piece here. Okay, so this is the cost function after we've done that substitution. But now we want to use that actual calculus to get our extrema. So we want to take a derivative, which gets us this 0.4 pi r minus 6.4 over r squared. And we can clean that up a little. So if I do like a common denominator, pull out that 0.4 and maybe even rewrite the 0.4 as 2/5, right? So these are all the same. I'm just sort of cleaning it up a little bit. But my goal is to know when this thing is equal to 0, right? Because that's where the max and mins occur. And that thing's going to be 0 at, all right, I can set it equal to 0, but that's going to be 0 where the pi r cubed is 16, right? Where the top is 0 up here. So I can solve for r there. Gives me this cube root of 16 over pi, which is some admittedly awful number. And I can plug that back into my h formula, right, which was 32 over pi r squared. So I just plugged in my r here to get that bit there. And this is my r and this is my h. Now, these are admittedly terrible numbers, right? Terrible values. But that's sort of the important sort of takeaway here is that like guessing or ballparking numbers would have never gotten you the optimal conditions. This is how we would get the optimal conditions, right? By going through this process. Okay. So what do we do? So we've seen general guidelines on how to solve optimization problems. And we went through this sort of soup can example. And these guidelines are good, right? They make a good framework to solve optimization problems, but every problem is a little bit different. So sort of from problem to problem, it may not look like a similar solution, but the overarching steps should be generally the same. The best way to really learn this stuff, though, is to make sure you do lots of practice. And to that end, watch all of the example videos and all the different, problems that you can. So that is that.